Hello, this is Jack Jackson. We're going to be looking today at an application of Bayes' theorem to a medical problem. So this is a homework exercise. So you can see a homework exercise that I have pulled up here in my stat lab or my math lab. So here's the problem. Suppose that 5% of the population has a certain disease. We have a test for the disease. 95% of those who actually have the disease will test positive. Okay, that's pretty good. But 13% of those who do not have the disease will also test positive. And so we want to figure out some different probabilities associated with this. And to get what we need out of this, we're going to have two trees. On the left here, we'll first talk about whether the first part will whether the person has a disease or no disease, and then whether they test positive or not test positive, test negative. Now the tree on the right will go this way. It'll say positive or not positive first, and then it will go from there to whether you have the disease or no disease. Now remember that we have, let's look at some given information. So let's put the given information in black. So we know that 5% of the population has a disease. So if we choose a person at random from the population, the probability that they have the disease is 5%. We'll do everything in decimals. And so notice we label the edge there on the tree. Okay, notice that the first thing here is just a straight probability. Probability of disease, probability no disease. Probability positive, probability not positive when you're pulling someone from randomly from the general population. Everything after that first set of edges has probabilities which are conditional probabilities. So we have a test that says that 95% of those, if you actually have the disease, will test positive. Well, that goes right here because that's the probability that you have a positive result given that you really have the disease. And that's what this conditional probability is here. So we get to this vertex here of positive only after we've gone through this one here of having the disease. So we know they've had the disease, and what's the probability they test positive in that case? 0.95. Okay. And then we also have, however, the probability that they test positive given that they don't have the disease, and that's hopefully low, and it's fairly low, 13%. A little higher than we'd like, but we have that. So that's the first thing that we come up with. Alright, now we're going to use some things that we know about trees to help us with the next bit of information. First thing we know about trees is that all of the probabilities coming out of a particular vertex must add to 1. So the probability of no disease has to be 1 minus the probability of a disease. So that's 0.95. Because these two probabilities here coming out of this vertex must add up to 1. Similarly, these two add up to 1, so this is 0.05 here, and that's the probability of no positive, in other words, a negative result given that you have the disease. A false negative. And these two also add up to 1, so that's 0.87. And what would that probability be? That's the probability of a negative result, or I've just been calling it not positive, so I'll call it not positive. Not positive given not the disease. Let's go here and erase this, and we'll go back to calling this That's not positive. Okay. So we have basically all the probabilities filled out on this tree for all the edges. So that allows us to fill out the probabilities at the end of the tree, which I'm going to put in red here. And this is a probability that's going to go right here. Well, what is this probability? It's the probability of D and P. D intersect P. In other words, the probability that you get that you both have the disease and test positive. And the way to get that is to multiply this, 0.05 and 0.95. So we multiply the probabilities along this path. Okay, which we have seen that earlier in our trees. So let's go ahead and pull up a calculator here, and we'll use a calculator a bit. Of course, we could do this by hand, but just save a little time. 0.05 times 0.95. That's 0.0475. So that's the probability that a random person would actually have the disease and test positive. Okay, so what goes here? Well, that's the probability that the random person both has the disease and tests negative, not positive. And we'd multiply 0.05 times 0.05. That's 0.0025. Here we multiply along this path, 0.95 times 0.13. That's 0.1235. What probability is that? That's the probability of not D and P. So, in other words, they don't have the disease and they test positive. That'll happen about 12% of the time. And then finally, the last one here, 0.95 times 0.87. 0.8265. That's the probability that they do not have the disease and they do not test positive. That's going to be most of the people, about almost 83%. Now, these probabilities for the N are for non-overlapping events, and so we can just add those up. And of course, if you add all of those up, let's just double check this, 0.0475. Okay, see if you can figure out what the answer is going to be before I hit enter here. Well, it better be 1. Sure enough, it is. Now let me show you one other thing. Look if I just add these first two probabilities together, 0.0475 plus 0.0025. Look what we get there. That's the 0.05 that we got from back here. So notice that these two are the only things coming from this vertex here at D, and so they must add up the probability that it takes to get to that point in our tree. So those two add up to 0.005. And likewise, these two here will add up to the 0.95. 0.1235 plus 0.8265. That adds up to 0.95. And of course, all of them add up to 1. Alright, well, so much for the tree on the left. Now let's look at the tree on the right. Okay, so far we know nothing about the tree on the right. Nothing was given to us. We haven't worked anything out. But the thing to notice is this probability at the end is going to be the probability of both P and D, or D and P. Well, we already know what that is. It is 0.0475. So this probability at the end for this path here, that we already know. Similarly, we know this next one is the probability of not D and P, or P and not D, and that's this one right here, 0.01235. And this one is here, probability of D and not P, and that was 0.0025. And finally, this one at the end, see, these are the same, these are the same, these kind of switch, they kind of flop in the middle. Not D and not P, that's 0.8265. So the probabilities at the ends here are the same in both trees. Okay, maybe in a different order, but still the same probabilities. This is going to be the key fact that's going to leverage working with the two trees. Now, once we have that, let's see if we can figure out anything else. Well, remember how these two probabilities add up to this one over here? Well, we can use that fact to add these first two probabilities to get this one, which is the probability of just a random person testing positive. So 0.0475 is the probability that it's a person with a disease testing positive, and then that's both of those things, and that this one is both a non-disease person testing positive. If you add those together, that's all the possibilities for a person testing positive, and so that's 0.171. No, yeah, that's correct. 0.07. Yes. Okay. Similarly, we can find this one here, the probability of not positive, by adding these two together, 0.0025 plus 0.8265. And that's 0.829. Of course, 0.829 and the 0.171 better add up to 1. So we can kind of check that. Okay? Or we could have just subtracted from 1 to find that. So we had a couple ways of finding that one. Alright, now what about the next piece? What can we do next? Well, let's see here. Okay, well, we know that these two probabilities here, this one is the probability of D given P. We know that these two multiply together to get this one on the end. So if we take the 0.0475 and divide it by 0.171, we will get 0.27 repeating. And that's going to be the probability of D given P. Probability that you have the disease given that you tested positive, about 28%. We can similarly, well, now we have two options to find this one here, this next one. We can do it by doing 0.1235 and dividing out by 0.171. Or we can just do 1 minus the 0.2 with the 7 repeating. Which is 0.7 with the 2 repeating. And that's the probability that you don't have the disease given that you test positive. Okay. Finally, we can do the similar thing down here. We can take this 0.0025 and divide it by the 0.829. And that's going to give us the probability right here, which is the probability of the disease given a non-positive result, negative result. So this is 0.003, well, whatever, 0.156815. Okay? And we can either do 1 minus that answer to get this one down here, probability of no disease given not positive. Very high there, 0.996984385. Okay, or we could have get the same thing by 0.8265 divided by 0.829. So again, I could check it by multiplying along the paths here to get the numbers at the end. Alright, so now let's go back and answer whatever questions they ask, because now we can answer all kinds of questions because we have everything filled out on both of these. What's the probability that a randomly selected person has a disease and tests positive? Positive and the disease. You'll see that in both trees right up here at the top, either here or here. Test positive and has the disease, 0.0475. Okay, so we make it, it's asking for a percent form, so that's 4.75%, and then it's asking us to round off to the 100th of a percent, so that's 4.75. What's the probability that a randomly selected person tests positive? Well, that's the probability of a positive result. That is, let me change colors here. That is right here, the probability of a positive, 17.1%. Hopefully that's what it says here. Yep, 17.1%. What's the probability that a person who we know is tested positive has the disease? 27.78%. That's right here, 0.02727727. So it's, or 2777777. So it's 27.7, bunch of sevens, 0.78 is where it rounds off. So 27.78%. Now, I want you to look at this because this is a very real problem. Many of you taking this course are probably going to be in some sort of health occupations. Not all of you, but many. And this is a very real example of how something happens, and it can often have a very unintuitive result. So notice that we have a fairly rare disease. Only 5% of the population would have this disease at any time. We have a really high rate of testing where 95% of those who test positive actually, 95% of those who have the disease test positive. That's right here. Okay. And we have a fairly low, maybe not low as we'd like, but a fairly low percentage of those who don't have the disease test positive. So it sounds like we've got a pretty good test. Okay? But because this population is so low that actually has the disease, only 5 people out of every 100, it turns out that this probability right here, okay, the probability that you have the disease if you test positive is only about 27%. It seems very low. This looks like it's 95% good on our test, and yet only 27-28% of them actually have the disease if they test positive. So now this is assuming this is a person chosen from random, not somebody who's coming in showing all the symptoms. So if we had something like a routine wellness exam and we tested for this particular disease and it tested positive, well, that doesn't mean that the person actually has the disease. In fact, they've got a much better chance, about a 72% chance of not having the disease, whereas they would only have about a 28% chance of actually having the disease. Of course, we would want to investigate further if we get a positive result. Watch the patient closely, see if there's some other tests that might corroborate this, look for symptoms, whatever. Maybe even start some treatment if it's appropriate. But we wouldn't necessarily assume this happens all automatically. There have been times when people didn't understand things like this and make some really bad decisions. For example, maybe this disease is really, really bad, that it doesn't have good treatment. And so a person, commits suicide based on the fact that they test positive on this, when actually there's only a 28% chance that they actually even have the disease. That would be a bad decision, or making some bad financial decisions based on that information. And they look at it and they say, well, there's a 95% chance that they have test positive if they have the disease. They confuse that with this conditional probability on the other side, the 28% chance that they have the disease if they test positive. So, there's a difference in those two conditional probabilities, but they're related to each other by looking at these two trees. And this is the essential idea behind Bayes' theorem and the Bayes' theorem type of reasoning. Okay. Now, let me just go a step further with this, and I can go a bit further with this. Let's see here. If we look at this and we break this into 4 regions, those who test positive, those who have the disease, of course this is positive and disease, this is not positive, not disease, we can put probabilities on each of these things. The disease and positive is right here in the middle, and that is 4.75%. Well, that's this one. Okay. Disease and not positive, that's this part, that's 0.25%. Positive and no disease, that's this one, 12.35%. And out here is not positive, not disease. That's the biggest part of the population, 82.65%. So that can be useful in kind of seeing where these 4 things lie. So if you look at a Venn diagram, we can label those 4 parts are the 4 red probabilities on the outside. We can also look at cross-tabulation tables and kind of put those, in positive, not positive, disease, not disease. And it might help you to see it in the table rather than in the tree. And we can put our totals along here. And of course, these 4 things that we just had are the 4 red probabilities that we just came up with. So positive and disease again was 4.75%. Writing percents this time, you could write them decimals or percents. Positive and no disease, that's this one, 12.35%. Disease and not positive, okay, 0.25%. And neither positive nor disease, that was the 82.65%. Of course, if you add these two together, you're going to get the probability. So here are totals. If you add those together, 82.9, that was showed up here, right here, in that tree. And the other one for positive is going to show up for adding these two together. That's how we found out that in the tree. Let's see, 17.1%. So if you remember, we added these together in the tab table. That's how we did it here. We added these. Whoops. We added these together right here. Come on. We added these two together to get this value right here. And that's what we're doing here in the table as well. And similarly, we can go over here and add across this way, 5% there, 95% here. Those were given. Those were this one and this one were given values. And of course, if you add anything up, of course, add everything up, you get 100% here. So there's our cross-tab table as well. So that has some of the information that's given here in this diagram. But really the diagram up here, the original tree diagram, has all of the conditional probabilities, all the intersection probabilities, and all the individual probabilities all together. So I personally think this dual tree diagram is probably the best way to keep track of it and to work through it. Alright, I hope that will help you with that problem there and with understanding these types of problems.